Okay, now we talked about using the FFT to do a linear convolution in the last segment. Now I want to take that kind of a step further. Here I have a finite length input, and I'm going to, and if it's a finite length, I can zero pad the arrays and get the linear convolution result. The trick is, if this is an infinite length, if one of these sequences is going on forever, I can only do a block algorithm to calculate my FFTs. And so that's kind of the story of the day, is how do I use an algorithm similar to this to calculate a linear convolution result, to actually do an FIR filter. Okay, and so let me start drawing that one out, and I'm mostly going to kind of wave my hands over here and draw the pictures, and I think we're going to let you go ahead and do the algorithm as a homework problem. So let's assume here, just like we did before, that I'm talking about an FIR filter. So this has m non-zero terms. So my impulse response is still finite length, okay? But my input, x of n, is long, okay? In in your labs, x of n starts up and goes on forever, right? Every second you get another 50,000 samples if your sample rate's 50 kilohertz. And so it ends up being very long, and I'm not going to process it in a single block of data. So we're going to assume it's long. It might be infinitely long. It might just be more data than what we want to handle in terms of doing an FFT. And so I'm going to assume that my time domain axis for x of n never ends, right? So I get a stream of samples coming in, and it's going to go kind of forever. Now, when I do a convolution, I'm going to break this thing up into n sample blocks. Okay, and I'm going to process these n samples using my FFT algorithm. So I'm going to take that n samples, I'm going to calculate an FFT of it, or a DFT of it. I'll use an FFT algorithm to come up with x of k, frequency domain samples. I'm going to multiply to get y of k, output samples in the frequency domain. I'll take values of my frequency response times x of k, multiply in the frequency domain to get the output signal. And so I get samples of my output in the frequency domain. I calculate an inverse, use an inverse FFT to come up with y of n samples. And I understand that when I do that, I'm going to actually be taking h of n and circularly convolving with x of n. Sorry, that's not right, right? This shouldn't be that. This should be n sample circular convolution, right? Okay, and then the key here is to understand that this y of n is not always going to be valid, right? Okay, so if I look at values of n here, I've just calculated values of y of n, and you know, if we think about that block of data that we would generate out of processing that n samples up, we should be getting samples out. Well, if this was m samples long and I do the convolution, the only time I run into trouble is right here at the start of the array, right? And at the start of this array, up here on x of n, oh man, I'm pointing up there. Let me say that again. So if I look at calculating y of n here, this block of n samples corresponds to a time domain block n samples up here in the x of n. And the key here is what I end up actually calculating is a circular convolution. And that means when I index into this array x of n, I'm always going to take the index modulo the number of samples. So if I need an index for x of n that's outside of the block of samples I use on the FFT, the sample value I would use when I index outside of that block is actually taken from the other side of the array, right? The index is always done modulo the block, right? So since everything is kind of the periodic extension of that block of samples. So what that means is when I do this convolution with an M sample impulse response, right here at the start of the array, that circular convolution is going to give me messed up answers because I'll be indexing outside of the block and just using the samples on the end of the block. Not what I want when I use a filter. Okay, so what ends up happening on my output sequence Y of n is I get a little group of samples out here that are bogus, right? But for most of the array, I'm going to get valid values, right? And I can actually predict exactly how many bogus samples I get at the start of this array, right? They're going to be, well, there's going to be m-1 values. It's the whole set where I would be, when I do the linear convolution, where I would be indexing outside of the array. If I have m samples in my impulse response, the first m-1 values here are going to be messed up because I need the values that are outside of the array. So if I look at the values of y, I get a group of valid samples out, right, when I do the calculation this way, and I get a set of values that I need to throw away. I get a set of values that are messed up because I've used a circular convolution instead of a regular convolution. That's a win for me, right? So that means most of my answer might be okay, right? And I just got to understand there's messed up values up here. And it means when I use these input blocks, I'm going to have to take a few more blocks. I can't just take n samples and then take the next n samples next to it and the next n samples and so on, because for every group of samples I get, I'm only going to get a finite number of a smaller number of valid output samples. And so the key here to doing convolution with long sequences is I don't try to deal with the whole sequence at once. I'm going to break it into n sample blocks. I know I'm going to get valid answers over some range of values. I know the start of this thing is going to be messed up. When I take my next block of data, it's going to overlap with the original one, so that when I calculate these values over here, they're going to be messed up, but I will have already had the answer from my previous calculation, right? Okay? And so when I take my incoming sample stream and I break it into n sample blocks, if I'm going to get away with using FFTs, these n sample blocks all have to overlap each other, right? Okay? And they're all going to be a total of n samples long, but they're going to overlap enough so that on each step here, I'm going to save the valid answers, and I'm going to understand that on the next step, those answers at the start of that array are messed up and are incorrect, right? Okay, and so that's basically what ends up being called the overlap and save method. And basically, overlap and save is a method of doing a linear convolution in the frequency domain, right? Using DFTs and FFTs, all right? And so let me summarize kind of how it works. Okay, so I'm going to assume that that in my incoming sample stream, if I look at x of n, right? I'm gonna use, you know, if I think about one of these blocks, so I have n samples here, okay, and I think about moving from one block of samples to the next, my next block of samples, so this is n samples long, is going to have here a total of m-1 samples, old samples, that I already processed in the previous block of data. These blocks have to overlap each other, right? Okay, and I have a total here of L new samples. Okay, all right. So I think of this n sample block being composed of old data because I know some of my answers are going to be messed up, and then And then my new samples here, I get a total of L values out to get the FFT size that I'm using in the array. This algorithm gives me x of k, right? Okay, I take that's an endpoint FFT to get x of k out, right? Then I'm going to calculate y of k equal x of k, h of k, right? And if I'm doing this in real time, I'm probably have done a single FFT. I'm not going to repeat the FFT every time for h of k. It never changes. I just take the values that I calculate out of this array and scale them, right? Okay, so there's my y of k out. Now I'm going to calculate an inverse FFT to get y of n out, right? Okay, and it's going to be a block of values that are also n samples long, right? It's an n sample inverse transform, but I have to understand these m-1 values. I'm going to discard. And this, I'm going to say that's valid, and that's what I'm going to save, right? Or write out to the DAC or whatever, or pass on to the next stage of the algorithm. There's going to be L samples. Okay, so on each step of this algorithm, and basically I'm just going to repeat that. On each step of this algorithm, I'm going to grab L new values from the input stream. I just leave the previous values alone, right? I save those. I grab L new samples. I produce L output samples. Same number of outputs as inputs. When I go back to process the next block of data, the next block of data has to preserve these samples when I tack on the values in the incoming data stream to form a total of n samples for the next block of data. All right? Okay, hopefully that was within sight. Okay, so that's the overlap and save method. Basically, that's the way to use FFTs to do linear convolution. So that's FFTs for linear convolution. And where one of the sequences is long. I'm still talking about FIR filters. Right, where h of n is a finite length. So if one of them is a finite length, I can deal with long lengths on the other sequence. So we'll take a break there, and then see kind of where that sets me up with my lectures. So.